Okay, on Monday, today's Wednesday, we were discussing, well, we started off by talking about the central limit theorem, and then we talked about the assumptions that are related to one sample inferential procedures. So when we talk about one sample inferential procedures, these are things like confidence intervals and hypothesis tests for the individual population mean. We then focused our discussion on the confidence interval. So we discussed how to construct a confidence interval if you have sigma or if you do not have sigma. And the exercise that we left off with was demonstrating the computation of a confidence interval when sigma was known. Now, to compute a confidence interval, we have to be familiar with how to work with the standard normal table and the student's t-table. Though to be fair, as we will see in a little bit, the student's t-table actually gives us, most often will give us the ability to find z-scores for confidence intervals when sigma are known, because it summarizes a lot of information on its second page. All right, so we were working on the exercise on slide 9. In this exercise, we are told that we have a simple random sample of 678 females. And then on average, this sample believes that 3.22 children is the ideal number for any family. So the sample value or the sample mean is 3.22 based off of the 678 females. So this would be the X bar for our particular example or exercise. We want to compute a 90% confidence interval for mu, given that sigma is equal to 2. All right, so the first thing that we have to do before we start our construction of the interval is that we have to check the assumptions of the test. The first assumption is that a simple random sample was collected. So we are told in the exercise that we have an SRS. So this is an easy assumption to verify. The second assumption is that we can assume that the population is normal, or we can assume that X bar is normal. We have no information about the shape of the population. And given that what we are measuring here is the ideal number of children in a family, I would expect that this distribution is actually quite right skewed, because most people are probably going to submit an answer between 1 to 3 children, and then you're going to have less families submitting answers of 4, 5, 6, or 7 children. So this is going to create a skewness within the population. Now, for our purposes, we can see that the sample size here is very large, 678 people, which is clearly much larger than 30. So therefore, we can assume that X bar is normal based off of the central limit theorem. So the central limit theorem is actually providing us with a way of verifying or checking off the second assumption of the confidence interval. Once we have the assumptions verified, we can work through the 3 steps that I outlined for constructing an interval. The first step is simply the computation of the Z value that will be needed. In this particular illustration, we are building a 90% interval. So our Z score is going to be the Z score that places 0.05 of the area under a standard normal curve into each tail. So we have 0.05 in the upper tail, which means that we would have 0.95 below it. When we use this 0.95, we can determine that the Z score is 1.645. From that, we simply have to plug into the formula for the confidence interval. So we have X bar plus or minus a Z score multiplied by sigma over the square root of n. So we will have 3.22 plus or minus 1.645 multiplied by 2 over the square root of 678. And this gives us 3.094 to 3.346. So this interval is telling us that on average, the women in this population believe that between 3.09 and 3.346 children is the ideal number. So somewhere in between 3.09 and 3.346. Now, from a practical point of view, we could say this kind of statements that we could make would be the ideal number, or females in this population believe that we would actually have to say something like more than 3 children is the ideal number for any family. Now, clearly, this is a suspicious conclusion because our interval only ranges from 3.09 to 3.346. And really, most of us would probably think that what this is telling us is that somewhere between or around 3 children is the ideal number on average, because obviously you have to have a whole number 1, 2, 3, 4, 5, this kind of idea. So the interval in this particular case is a little bit more difficult to interpret in a very contextual or a very contextual or applicable way. Really, what it's telling us is that slightly more than 3 children is the ideal number, but that really doesn't have make a lot of sense in the context of what we are actually studying, unfortunately. Now, in a very strict interpretation, we can just use our general explanation of a confidence interval, which would be we are 90% confident that the true mean number of children that this population of women thinks is ideal is between 3.09 and 3.346. So that's our strict interpretation of the interval. But if we wanted to try and explain the result to someone, it would be difficult because the interval is implying that more than 3 children is the ideal number on average, but it's not actually, it doesn't contain 4, which would be the next logical number above 3. Okay. All right, so any questions on that idea regarding the interpretation and whatnot? All right. Okay, so we have a few more problems left to solve. So for example, in part C, it asks, is the interval valid? In part D, it asks, what is the length? And then in part E, it asks, why are we 98% confident and not 90% sure? Okay, so for part C, is it valid? So when we talk about validity, we're really just talking, we're really just asking, did the assumptions of the interval hold? So yes, it is a valid interval because the assumptions are intact or hold. In part D, it asks, what is the length of the interval? Length of a confidence interval is simply the upper bound minus the lower bound. It's the same thing as asking, like, what is the range of the interval, or what is the difference between the upper and the lower bound? That would be the length. So in this particular case, we would have 3.346 minus 3.094, which is 0.252. Okay, and then in part E, we were asked, why are we 90% confident and not 90% sure? This, again, going back to what we had talked about last class, our interpretation is based off the idea of repeated sampling, period. So we do not know if this interval captured mu, but we are confident that, for example, 90 of 100 CIs built using samples of size 678 would contain U, right? So we are 90% confident and not 90% sure because we don't actually know if the interval we constructed contains the population mean, but we are confident that if we were to, for example, build 100 or 1,000 or 10,000 different confidence intervals from samples of size 678, that 90% of those would contain the true mean. Any questions about that? Okay, so exercise 2, a simple random sample of 604 males felt that 3.06 children was the ideal number. Compute the margin of error for the corresponding 95 and 99% confidence intervals given sigma is equal to 2. Will the 95% or 99% confidence interval be more accurate? Explain. All right, so the margin of error for a confidence interval is everything that sits to the right-hand side of the plus minus. So in part A, we would have the margin of error, which we designate as capital E, is equal to Z alpha over 2 multiplied by sigma divided by the square root of n. Okay. So we have to work out the Z scores for both the 95% and the 99% intervals. To do this, we can actually save a little bit of time if we use the student t-table, which I will show to you now. Okay, so the student t-table will be located on the course website, and it has 2 pages associated with it, which are labeled page 1 and page 2, or part 1 and part 2. So this is page 1 of the student t-table, which gives us our t critical values for different degrees of freedom. And I'll come back to talk about this and refresh you on this idea in a little bit. The reason that the t-table can be very helpful, though, is because on page 2, it actually gives us Z scores at the very bottom of the page. So you can see, for example, the Z score that we computed last class for the 90% confidence interval, the Z subscript 0.05, we showed why this is equal to 1.645 using the standard normal table. The student t-table gives us exactly the value of 1.645 at the end of page 2. So this is a sort of a shorthand way for us to skip through having to do that particular type of computation or calculation every single time. Now, in the context of the question that we are working on, we are going to consider, sorry about that, we are going to consider the 95% and the 99% margin of error. Okay, so we would have 95%, 99%. So in this case, alpha is going to be 1 minus 0.95, which is 0.05. So therefore, Z alpha over 2 will be Z 0.05 over 2, which is Z, which is equal to Z 0.025. And then the 99% interval will be alpha is equal to 1 minus 0.99, which is 0.01. So then we're going to have Z alpha over 2 is Z 0.01 over 2, which is Z 0.005. So from the second page of the student's t-table, we can directly compute both Z 0.025 and Z 0.005. So we can see here, Z 0.025 is 1.96, Z 0.005 is 2.576. So on this slide, we now have 1.96 and here we have 2.576. Okay, so our margin of errors for the 95% and 99% confidence interval will be computed in a very similar way. We're just using a different z-score. So in the case of the 95% interval, we'll have 1.96 multiplied by 2 divided by the square root of 604. And this is going to give us 0.1595. And then for the 99% interval, we'll now have 2.576 multiplied by 2 divided by the square root of 604. And this is going to give us 0.2096. So the margin of errors, again, are simply what is to the right of the plus minus sign in the equation for the confidence interval. In part B of this question, we are asked to determine which interval is more accurate. So when we are talking about estimates, or estimators rather, for a population quantity, the idea of being accurate means actually being close to the population mean. So really what I'm trying to ask in this question is which interval is going to be tighter or more precise would actually be the better language to use in this particular question. So accuracy refers to being close to the population mean. The truth is we don't know, again, whether or not either of these confidence intervals contain the population mean. But what we can do is talk about the precision of the interval based off of its length. So if we were to just make a slight alteration to this part here and ask about precision, so which one will be more precise, then to answer this question, what we can say is the following. Since E for the 95% interval is 0.1595 and E for the 99% interval is 0.2096. We then have X bar plus or minus 0.1595 and X bar plus or minus 0.2096. So the interval for the 95% confidence interval is going to add and subtract a smaller value than the interval for the 99% interval, or than the value that is added in the 99% confidence interval. Okay, so this will lead to okay, well, we can explain it like this then. So, well, we know that the length of the interval is the upper bound minus the lower bound, right? So then we can say length is equal to X bar plus 0.1595 minus X bar minus 0.1595. So this is going to be 0.1595 plus 0.1595, which is equal to 0.1911113. And then what this shows us is that the length of a confidence interval is actually just 2 times the margin of error. So for the 99% interval, we can then show that length is simply 2 times E from the above derivation. That's going to give us 2 times 0.2096, which is going to be 2 carry the 1, 9 carry the 1, 1, and then 2 times 4, 0.412. So now what we can show is that since the length of the 99% interval is bigger than the length of the 95% interval, that means the 95% interval is actually more precise than the 99% interval, since precision defines closeness of or a shorter range in the context of the interval. So since 95% interval is shorter or not as wide as 99% interval, it is more precise. So you might recall from your previous studies the idea that there's a trade-off between the confidence level and the precision of that interval. Or you might recall or have thought to yourself at one point, okay, why don't I always just use like the highest percent confidence interval? The reason is for the same sample size, as you increase the confidence level, you sacrifice that precision. So the 95% interval is technically going to give you will give you a shorter range in which the population mean exists. Whereas like a 99% interval in comparison to the 95 is going to give you a much wider, will give you a wider range for where the population mean exists. Okay, the last question is simply an interpretation of the margin of error. So on the previous slide, sorry, I'm just going to flip back here. We have for the margin of error, our interpretation would be something like we are 95% confident that the error made in estimating mu by x bar is at most 0.160. So in the context of our problem, we could write something like we are 99% confident that the error made in estimating mu by x bar is at most 0.20, or let's just round it to 3 decimal places, 0.210. So those are some examples of working with a confidence interval based off of the Z-score. But the ideas that we have established in the exercises that we had just worked through, so the ones on slide 12 here and starting on slide 10, these concepts extend across both the student T and the standard normal confidence interval. So the computation of the length, the comparison or the sacrifice of precision for increasing confidence level, that will be true whether you use a standard normal or a student T interval, as long as the sample sizes between them are the same. If you are able to increase sample size, then you would see potentially a higher percent confidence interval with the same length as a lower percentage confidence interval. Because sample size, as we know, decreases the margin of error. So an increase in sample size means that there's less sampling error, which means that we would increase precision in our estimating techniques. So on slide 13, I just have some summarizing points of the exercises we just worked through. So the definition of the length, how the margin of error is going to change with each of the different constants that make up its computation. So how confidence level, standard deviation, and sample size affect the margin of error, and then of course would affect the length of the interval. Again, the big things to keep in mind are when everything is constant, changing the confidence level will increase the margin of error. Changing or increasing the standard deviation will also increase the margin of error. Increasing sample size will decrease the margin of error. And from a a conceptual standpoint, the last 2 points in particular make a lot of sense because increasing sample size means that you are collecting more information from the population, which would naturally improve your estimation because you have more information. Whereas, or similarly, if you are observing a population that has a very large standard deviation, has a very large standard deviation, then precision of the interval is going to be affected because you have such a wide range of area that you need to cover in order to, or when computing your interval estimates. Does anyone have any questions at this point? Okay, so most often we are going to deal with situations when we do not have a value for mu or for sigma. So sigma will have to be estimated by the sample standard deviation. The formula for the sample or the defining formula for the sample standard deviation is given on slide 14. So when we do not have sigma, but we have our sample values, we have to go through the process of computing little s so that we can utilize it where sigma is usually placed within the confidence interval. It turns out that S squared is an unbiased estimator for sigma squared, which means that it's a very good estimator for sigma squared. And it also means that in terms of the notation that we had just discussed very briefly in lecture set 1, that the expected value of sigma squared or of S squared is equal to sigma squared. Interestingly, little s is actually not unbiased for sigma. So S squared is unbiased for sigma squared. So the sample variance is unbiased for the population variance, but the sample standard deviation is not unbiased for the population standard deviation. Sort of just a little aside. Okay, so the student t random variable results from what is called the studentization of a random variable. So remember that the definition of standardization means taking a random variable, subtracting its mean, and dividing by its standard deviation. If x bar is our random variable, then we would subtract the mean of x bar and divide by the standard deviation of x bar. This leads to what we have in equation 1. Now, if sigma is unknown and we have to replace sigma with little s, then equation 1 turns into equation 2, and now what we have is the studentization of x bar. So we are no longer standardizing, we are studentizing. And the result is that equation 2 is not standard normal distributed. It follows what is called the student's t distribution, which is very similar to the standard normal distribution. And in terms of the techniques that we're learning about, what this means is that our confidence interval now has to be based off of the student t random variable rather than the standard normal random variable, and that the hypothesis test that we'll see a little bit later used the student t table critical values and p-values rather than the standard normal table critical value and p-values. Okay, so as a refresher, on slide 16, we have an illustration of both the standard normal and the student t distribution. So the red curve here is the standard normal density curve. And the black curve here is the student's t curve. At a low degree of freedom. Okay, so the standard normal density curve has 2 parameters associated with it, the mean and the standard deviation, which we typically call mu and sigma. The student's t density curve has 1 parameter associated with it, which is what we call degree of freedom. As the degrees of freedom gets larger, the student's t curve begins to take on the shape of the standard normal. So when the DF increases, we have an increase in the peak and a decrease in the tails. Okay, so as our degree of freedom gets larger and larger, the T curve essentially pushes inward such that the peak would increase and the tails would come in, and it will grow to match the standard normal curve. So for a very high degrees of freedom, which is the same thing as saying a very high sample size, the student T values and the standard normal values are essentially indistinguishable. And actually, once we look at the student T table in a little more detail, you will see that the table reflects this property. And then when DF decreases, we have the opposite effect. So when the degrees of freedom gets smaller or the sample size gets smaller, your tails basically push out and the peak comes down. So the idea is, especially for lower sample sizes, the student's T curve is kind of protecting you from the unknown population standard, or from the fact that you do not know the population standard deviation. So this lack of certainty about the true variation in the population is being accounted for by a larger critical value that's going to give you a wider spread, like in your confidence interval for illustration, because you'll be multiplying by a bigger value. Okay, so in terms of computation of the confidence interval, using the student's t-table does not add a lot of complexity to our calculation. The only real difference is that where the z-score was once utilized, we now use the student t-value. And typically, actually, students find working with the student t-values and the student t-table much easier than the standard normal table, because the table presents the critical values in a very upfront manner. The assumptions for the interval will be exactly the same as they were for the interval based off the standard normal curve. So there's no difference between how we go through the checking process when we're using a student t versus a standard normal interval. The major difference, again, is just that we will be working with the student t table rather than the standard normal table. All right, so as an example, let's suppose that we are interested in measuring the population mean of the theoretical spring constant for type 1 springs. So we have a simple random sample, we have 6 type 1 springs, and from the sample, we have a mean of 2.03 and a standard deviation of 0.068. We want to construct a 95% CI for mu. First, we would check our assumptions. The first assumption is that we have a simple random sample. So you can see here in the first sentence, I'm indicating assumption 1, which is the SRS, and we can check that off. Now, the second assumption is that we can assume a normally distributed population, or we can use the central limit theorem we can use the central limit theorem to assume that X bar is normal. We only have 6 observations in this data set, so it isn't reasonable to use the central limit theorem, as that requires at least 30 observations. An alternative is to use a normal probability plot of the samples to determine if there's evidence that the variable of interest is normal. The plot here is titled normal QQ plot. So this is the normal probability plot of the observations in our sample. You might recall a normal probability plot from your earlier studies, but if you do not, essentially what we are doing here is we are checking to see if the observations in our data set form a linear relationship with the theoretical values from the standard normal curve. The theoretical values can be found in a number of different ways. There are tables that you can utilize, but in this course, we will always compute the normal probability plots using SPSS, or they will be given to you. So we're not focused on the construction of these plots, but simply on how to utilize them. So the plot here shows us that the observations are forming a straight line relationship with the quantiles of the normal distribution. So you can see in the plot, we have our 6 values. They're not as tight to the line as you might hope they would be. Ideally, they would fall right on top of the line. But what we can see is that there's no evidence of a curvature or a non-linear pattern. Okay, so plot does not show evidence of curvature or non-linear relationship. All right, so it shows basically a straight line pattern. This straight line pattern would indicate that there's evidence of normality. So this would be more or less what we would like to see when we use a normal probability plot. Again, ideally, the observations would actually sit right on top of the line and we would have a larger sample size to work with so that we could see more of a pattern. But in this case, when we only have 6 values, it seems like the assumption of normality is reasonable for this particular, based off of this sample. So our second assumption, which is normality, which is indicated here, we can again check that off based off of the normal probability plot. So this is another tool at our disposal that we can use to check for normality. Yeah, okay, so that's a good question. So for question 8 on the assignment, you would have, so for question 8 on the assignment, in the second assumption, you would have to write something like, we are unsure if the data is normal because we don't have any evidence of normality and the central limit theorem does not apply. So we could check this using, for example, a normal probability plot. And then you can just go through and carry out the computation. And on step 3, you can just write something like, if normality can be verified, then we are 95% confident, and you can finish off the question. Does that make sense? Yeah. So it's a conclusion with a condition that that assumption can be checked. And I should have some examples of that coming up as well. Okay, so now that we have checked the assumptions, we can work through and use the student t-table to complete our interval. So on step 1, we're just finding the parameters for our t variable. So we're using a 95% interval. So alpha is going to be 1 minus 0.95. So alpha over 2 will be 0.05 over 2, which is 0.025. And then our degree of freedom here is going to be n minus 1, which in this case is going to be 5. So the student t-table, again, this is typically the preferred table, is really just a table where you have to match the one value in your subscript to the other. So in our subscript, we had t 0.025. We have 5 degrees of freedom. That gives us a t value of 2.571. So the 2.571 that was found, or that was shown on the slide, that's just a result of matching 0.025 to 5. Okay. Now we simply have to plug into our expression. So we have x bar plus or minus the t value multiplied by s over the square root of n. So plugging in the values from our example, we end up with an interval of 1.959 to 2.101. So then we can say on step 3, we can be 95% confident that the true mean, or the population mean theoretical spring constant, is between 1.959 and 2.101. Does anyone have any questions about the example? All right. Okay. So using the same information from the previous slide, let's compute a 90% CI for mu. So again, we would start off with the assumptions here. Since we are using the exact same data set, we already know that both assumptions will be intact. So Our simple random sample assumption is verified because we had an SRS of 6 observations, and we've checked off normality based off of the normal probability plot. So on step 1, we have a t-value on alpha over 2 comma n minus 1. This will be a t-value on 0.10 over 2 comma 6 minus 1. This will be a t-value on 0.05 and 5. So if we go to page 1 of our student t-table, we are matching 5 to 0.05 to get 2.015. So the t-value for the interval that we are working on, which is the 90% interval, we'll use 2.015. All right. And then on step 2, we're simply plugging in. So here we're going to have x bar plus or minus t 0.05 and 5 multiplied by s over the square root of n. So that's going to be 2.03 plus or minus 2.015 multiplied by 0.068 divided by the square root of 6. And that will give us 1.974 to 2.086. Okay, and then on step 3, we can write we are 90% confident that the true mean TSC is between 1.974 and 2.086. Okay, then it asks us, will the 90% CI be wider or narrower than the 95%? So as we learned in the previous illustration, or in the example before we started talking about the t-distribution, the width of the interval is directly affected by a change in confidence level. So for the same sample size, we will observe a more precise interval as the confidence level decreases. So we can say, without even actually having to do the computation, though you could easily verify this by subtracting the lower and upper bounds in the 2 previous examples, the 90% CI will be narrower than the 95% CI, since both use little n is equal to 6, and the 90% CI is, and the 90% CI uses a lower confidence level. Right. So again, if sample size is constant and the other parameter in this case, which would be S, is constant, which they are, a 90% CI will naturally be narrower than the 95% CI because you're multiplying by a smaller t-value. Does anyone have any questions? All right, so on slide 20, I just give a little bit of more of information regarding the computation of the probability plot. But again, this is not something that you need to focus on or even really dwell on at all, because we will be constructing normal probability plots using SPSS throughout the course. And if you need them, they will be provided to you on tests or the final. In the context of a question like question 8 on assignment 1, if an assumption cannot be verified, you should suggest a method for verifying the assumption and then adjust your conclusion accordingly. So this goes back to the question that was just posed a few minutes ago about how to handle question 8, where the sample size is only 25. So at this point, it's clear that the central limit theorem won't take over, and our conclusion will be affected by whether or not we can confirm normality. We can still go through and complete the question and give the confidence interval, but we should also conclude that we need to find a way to, or we need to actually build the probability plot to check to see if this is valid. Okay, so the CI again is simply, it is truly an estimate, but it's a range for our estimate of the population mean. So it's giving us two values that we believe the population mean falls in between. It's more effective than the individual point estimate. So the CI is preferred to X bar, for example, because it accounts for the sampling error. So we are taking into account more information about the population structure than we would be if we just provided X bar, for example. We have two different ways of computing CIs. We can use the standard normal table or the student t-table. And again, this just depends on whether or not we have population standard deviation or we do not have population standard deviation. Okay, on slide 22, I give a cumulative exercise for you guys to try by hand. This doesn't require any computation. This is just a higher level sort of exercise that asks for you to suggest ideas for accomplishing the goal of this particular experiment. So when I post the completed slides, I'll also post answers to this cumulative exercise for you to review. So the suggestion is to try this for extra practice. All right, so we can move into hypothesis testing. We have a few minutes left, so I'll just briefly touch on the idea here. The confidence interval provides us with a range of values for which we believe the true mean will fall in between, or we can be confident that the true mean would fall in between. The hypothesis test is a procedure that allows us to ask a question about the population parameter. So in general, the types of questions that we would ask are always based around whether or not the population mean or population parameter is greater than, less than, or different from a certain value. So all of our hypothesis tests are formulated around the idea of being greater than, less than, or different from some number. Now, in the context of one sample tests, we are always comparing the population mean to some pre-established constant. In the context of two sample tests, which we will talk about in lecture set 3, we are comparing population means to one another. So a lot of the time, the kind of questions that we can ask in the two sample case almost feel more intuitive or more, what's the word? They are more interesting, I guess you could say, than the one sample test, though this isn't always the case. So for example, we might be interested in asking in the one sample context. So for question 3 on slide 24, it says, is the average amount of liquid in a 2-4 of beer equal to 330 milliliters? So this would be a very standard kind of one sample hypothesis test where you're comparing the average amount of liquid in a case of beer to a pre-established value that must be contained within each bottle as it's labeled with, say, 330 milliliters. All right, so on Friday, we will go through the process of conducting a hypothesis test. We will look at some examples and some illustrations, and we will talk about how we would approach these in both the case where sigma is known and the case where sigma is unknown. We'll also review p-value calculation based off of the student t-table and the standard normal table. So if you guys have any questions, as always, please let me know. And if not, I will talk to you guys on Friday at 1 o'clock. And as a reminder, the assignment is due Friday at 11:59 p.m. via CrowdMark. And if you have any issues accessing CrowdMark, please let me know and I will try to sort those out for you before Friday. So have a good one, and I'll talk to you guys later.